I'm Motiejus Jakštys, a senior backend developer at Spil Games. Today I'll speak about large partially connected Erlang clusters. So first, we have a quite sufficiently big service-oriented architecture backend infrastructure. Infrastructure provides API to render our portals. Numbers, a couple of dozen beefy servers running roughly 50 services each. You can do the math to imagine how many nodes we have in total. Agenda, I'll give a historical introduction and then technical stuff. Please interrupt any time, feel free, sorry. And there will be a QA session at the end, but let's talk. So my point today, I'm going to make a point that management of big battles is very similar to management of big distributed systems. And I will actually present you a battle which happened in history. I have a good example, which is Battle of Stalingrad. It's a turning point of the Second World War when Hitler was fighting Stalin. That was really the fight between those two. After this battle, Germans started losing. So it was the first major Hitler loss in the East. This flag is a Soviet soldier holding the Red Army soldier holding the Soviet flag at the end of the battle when they won. You might want to ask, why did I pick this example from, I don't know, 70 years ago? We didn't really have computers then. We do now, but there are quite a few examples we can learn from the battle and the management of the battle. So why is this battle interesting? To begin with, this is a rubble battle. This is one of the major modern rubble battles in the history. What does this mean? That means that German fleet, the Luftwaffe, destroyed the city completely in the very beginning of the battle. So the rest of the battle was carried out by soldiers in the rubble. This brings a few interesting consequences. For example, when there is rubble all over the place and the area is quite small, the maps are useless, so it is impossible to determine the location. GPS wasn't there yet, so the location was really ad hoc. So that led to peer-to-peer communication between the soldier groups. So whenever a soldier needs supplies or reinforcements, they ask for another group on the left, on the right, on their back, and then the message is sent verbally, because radio is not reliable, slow to set up, and useless because of the small distances and impossible to determine area. That's peer-to-peer communication. Then another property of the battle in general and army, that it's very heterogeneous. So we have infantry, we have tanks, we have air force, medical staff, commanding staff. They all work differently. They have their different ways of communication, they have different ways of doing, but they all work towards the same goal, is to win the battle. So, communication channels, meaning that in the army, there is a very clear hierarchy who reports to what and who communicates to what. You don't want a general taking care of 200,000 soldiers or 200,000 soldiers reporting to a general. Please refer to a CEO and people of large companies. That's also true. I'll get back to that. So in army and in battle, we know clearly who communicates to what. It's not like everybody speaking to everybody. Dynamic environment of the battle. So tactics and the situation of the battlefield change the dynamics all the time. So areas are lost, areas are captured, equipment dies, and new equipment is got into place. So it's very, very dynamic and changing all the time. And you have to take care of this change. You meaning the generals, the people who manage the battle. Another thing, it is not enough to take care of your business, of your small area, in order to win the battle. All units must work together, combine, to achieve the same goal. That tanks have to help infantry, infantry has to, airplanes, the bombers have to help everyone. And there has to be a way to communicate the tactics, to communicate the goal to everyone. And this deserves an example. So this is this situation in November 15th, You see the Stalingrad city is at the middle. Germans at that time had 90% of the city. Both sides were pushing a lot of people, a lot of resources, but Russians, Soviets, excuse me, there were no Russians at that time, Soviets were taken out. So both sides had a lot of causalities. A newly arrived soldier's life expectancy, Red Army soldier, was less than a day. So if you come to the battle, you pretty much die the same day. That's the average. Officer, 3 days. And as I told you, Germans had 90% of the city. So situation of Soviets was really bad. Why? Another interesting fact about this battle, so why did it happen? It is tactically not that important, the city. But both sides were plunging huge resources to it. And the real reason was because the city had Stalin in its name. So it was a battle of pride for both. Hitler wanted to take it because it's Stalin, and Stalin wanted to defend it so badly. Otherwise, they could have just given it up and go on. That's why it's also interesting. So within a week, Soviets saw that their situation is really bad, and they made up a plan, Operation Uranus, which surrounded the whole army, the whole city. So they surrounded, there was in the middle, over here, there was over 200,000 soldiers. You can imagine you have to feed them. You have to provide weapons, everything. So they cut off the supplies, and then that was the time when slaughterhouse started. So they were destroyed. And this was the first major loss of Hitler and turning point of the battle. So this is a big plan. You see, it really involves a lot of units. So these units had to be communicated somehow. It has to happen in the battle. And I'll get to the cluster, why it's important. So the city was Germans for a while, but Germans were Soviets, and they were done after a while. The battle finished quite soon after this moment. 6th Army was a major German army. It was destroyed. So you see the introduction, the historical introduction, and you might wonder what does it has to do with clusters? It has a lot. So we have a lot of, in our environment and Spil environment, and probably many yours, we have a lot of different nodes which are trying to achieve the same goal. Usually it's to serve the customer. Is it internal, external? It doesn't really matter. You have to serve the customer. A reminder for the background, what kind of a cluster we have at Spil is 50 nodes per cluster and a couple of dozen of servers. That's way more than 100 Erlang nodes. Example services, what we run there is high score, authentication, chat, user profiles, and so on. So we have different applications doing different things, but they're all serving our portals, they're all serving our customer. The question I'm answering today is how do we connect them so it all works? First, peer-to-peer communication. This title probably looks familiar from a few slides back. So the reason for peer-to-peer in the cluster is we don't want bottlenecks, we don't want a middle party because it's slower, and we don't want single points of failure. So if you have, well, you just want services to talk directly. There's no reason for them to do hops. Clustered environment is also dynamic. I think you can agree here. Services and nodes start and stop all the time. They are started or stopped because of the requirements that you just don't need that many resources at 3 AM. Or they also die. Machines die. Networks die. And because of the dying and because of the changing all the time, system must continue to serve. System must heal itself, just like in the battle. Partially connected network. So I told you why you don't want to connect everything to everything. And now I'll prove you by the numbers. So we say we have n as a number of nodes. So total number of it's overhead, it consumes memory, and it's very tricky to isolate any problems if you have everything connected to everything. So also isolation. So conclusion, in general, both in clusters, in the army, in management, software-defined networking, it pays off to optimize your network topology, so it doesn't speak to everything. Doesn't speak to everything. We had an OpenShift woman at the keynote. This is software-defined networking. This is something she's working on. So this is all over the place. Army management. And how do we do this with the piece of software that I'll show you now? Again, the requirements that we want from both Battle Army and Erlang cluster. So peer-to-peer, multi-application groups, dynamic nodes, and connected network. And because the requirements are kind of the same, and you are, I believe most of you are distributed system developers or maintainers, we can be generals. It's the same thing, right? So there are two mainstream applications that help you services without affecting the cluster. But partially connected network is something they don't do. And this is something SPAPI router does. It's very simple, and I'll show you how. So features, shortly, like I told you, it creates a mesh network. In our case, it connects hidden nodes, like configured, the way the topology is configured. Abstracts the destination. So instead of calling a different node, you don't want to call a different node. You want to call a different service. So it's like RPC call, but the first argument is not the node, but the service, what you're interested in. And SPAPI router takes care of looking which actual destination you want to call. We believe it's pretty good. We've been using this for 2.5 years in our backends. We optimized it. We fixed bugs and issues, and we trust it. Instrumented. I'll speak about instrumentation after a little bit, why you want it and how you achieve it here. Let's say you have, oh, by the way, any questions up till now, either about the battle or the nutshell features? I have two, great.
How big was the forces of the Red Army in this battle when they surrounded Stalingrad?
Way more than the ones inside the city. You could see that outside. Outside there was quite some Germans, Hungarians, and Romanians. But inside the city was the major force. There was also another battle after this. But this is kind of really historical, so let's speak together after this.
Okay, thanks.
It's interesting, but let's keep it. Another question?
Yeah, I have a question about because there are also global groups, right? That partition
yes.
a set of nodes. I was wondering why they weren't mentioned as well.
So the global, you're right. Here is the table. So global could also be put here, also for the same three. Oh wait, global can partition the.
I'm not talking about global, but global groups.
Global groups is something Release is working on?
No, it's an OTP. They partition, so instead of having a fully connected network, you can have a partitioned network.
In that case, you need to hop. Well, if I understand correctly, in that case, you need to hop. You cannot connect to direct. Well, you partition by service, and we don't want to do that. So with global, you have to do hops if you want to reach the same destination. Is that correct? So the problem is you have to do hops, otherwise you won't be able to reach your different applications. If I understand correctly how the global works.
No, I don't think so. Anyway, we'll talk about that later.
Okay. Might be missing something.
Oh, that's another one.
Another question.
Yeah. I would like to know why to put 50 nodes, 50 Erlang nodes by node, and not one Erlang node by machine.
That's a design decision. So we can also chat about this later. I think I made the. I should have done questions at the end because they required the elaborate explanations. Yeah. So I'll tell you about that. We have a reason for that.
No more questions.
Yes. For clarification, please raise your hand and let's talk. But questions at the end, because I see that it's not that easy to answer in a second. So let's get back. So a library creates mesh network, abstracts the destination, mature, instrumented. Let's take an example. We have three machines here. You see they're different color coded. The first machine is a page builder. So let's assume that we're building a web page. The web page consists of two parts. This is a header and the main section. So obviously the main section requires more computing resources. And the way we build them is the page builder requests for two different parts. So for header, here, page builder, header, main section. So requests two parts and then concatenates them together, and then here you have a page. But the thing is that the sub-pages, these ones, they don't have to know about each other. They're completely independent. So this is one example, and this is exactly what we do at Spil, one of our backends, when we're building the pages. We have a tree, a hierarchy, how the pages are built. There are also so these also are obviously sub-pages, so they delegate work more. And we want to connect it this way. And you see there's this thing, it's not connected. The reason is that the node name is test2, so you don't want testing to intervene. So there's a particular way you name your nodes, which you connect to. That's also part of the answer of the question. This is an example configuration, how you configure this component. So you see where you want to connect from, sorry, others, where you want to connect from, you configure, you put SPAPI router there and connect to the other nodes. So in this case, we have two hosts, host 1 and host 2. So these are the two bottom ones, where it connects and looks for the destinations. And then we have, so it connects and looks, is there a node where I want to connect on this host? So it connects to, it looks for workers which match this regexp. So this is the regexp of the node name. So you can see header and optionally a number. So we have header, we don't have a number. So this matches this regexp. This header, the atom in the list, is the application that has to be running on that node. If there is no application running on that node, then it's not a service, you're not interested. So there might be a problem, there might be a different thing, you don't want to use that. Same for main section. So main section, the node name, and main section, the application name. If these hosts match these node names, here as well, and with which node names have the running applications, voila, you're connected. Pretty simple. There's more configuration stuff here, which is useful. You can change the frequency, how often do you want the hosts and applications monitored. I won't speak about these. These are in the paper, which is next to the application you'll see at the end. I'll speak about callback module a little bit later. So in detail, how this works. Let's reiterate. First, SPAPI router, a node running SPAPI router, which is a library, a reminder, it works aside to your application. It connects to these two nodes. Then it connects to EPMD of these, it connects to EPMD of these two machines. It asks for the running nodes on that machines. If the nodes match the regular expression, then it connects to these nodes, matching the regular expression. Then it checks running applications on that nodes, and then stays connected to the relevant nodes and disconnects from the non-relevant nodes. I think like 10 people here, or maybe half of the audience, have a question, is it a race condition? Yes, but we don't care. So this is how it works, and this is the instrumentation bit. So A, I will give you the reason for instrumentation. B, I'll show you how easy it is to instrument your application if you're running SPAPI router. So in any instrumentation talk, the very first thing they say, you want to instrument the borders of the system first. So anything that's coming in and coming out, you want to instrument first. Then instrument, meaning that you want to know what's going on. So the time it takes to do something, the number of OKs and errors, and other kinds of internal things. The amount of traffic transferred is the first thing that you put on your production machines when you can see time series. So you instrument the border of your host. And this is exactly what SPAPI router does by default. So for every outcoming call, you see the time it takes to execute that call and how many OK and erroneous calls are happened. This graph is a random graph from our random service. It shows the number of requests per second. The greens are OK and the reds are errors. The graph is not particularly interesting now because everything's healthy. You see it's 24 hours, so it's okay to 4 a.m. there's lower traffic. But in case there are errors, you see something immediately going wrong in one of the graphs, that the calls are failing, the services are down. Something is going bad. And my point is that with SPAPE router, you get this for free, as long as you have somewhere to instrument to, but that's another thing. You probably have, everybody has Graphite or something like that, log servers. So this is how you implement those instrumentation and user callbacks. So one thing, you can attach user callbacks to your, when you get a new resource and when you lose the resource, you can react to it. So when there's a new service, you can change the state of your program. When there's a lost service, you also can change the state of your program. This is a proper Erlang behavior. And all instrumentation is done with 3 functions. So function measure, which measures the time it takes to execute the call. And the success and failure are simple counts. We put these counts to Graphite cluster. And then with these success and failure, you get the graph that you saw just before. So here's how you do callbacks. API. So you have your library, you have your dependency set up, you have it configured, you have your cluster connected. How do you use it? It's very simple. Oh, sorry, I didn't change this thing. So instead of PeertoPeer, there should have been header or main section. I am a fan of PeertoPeer, that's what it was here. So SPR router call, then header or main section. So this is the service that you are calling. And then module function arguments. So this is exactly the same as RPC call, but the first argument is not the node, but the service that you're interested in. Then there's call all, which is a broadcast. So it calls all the services with this name in your cluster, synchronously. There are more functions, so call and call all with arity 5, which get extra options. For example, asynchronous call, timeouts, and pretty much everything that is in the RPC module we modeled after it. There's one optimization for this call, is that if there is a node, an interesting service on localhost, it calls localhost, otherwise it calls a random service. This is very useful to reduce network traffic. So, future optimizations, things we can improve, but we didn't need to or didn't have time for. For the client, since this is a one-way application, meaning that only the, so let's get back to a very long, no, quite long ago. You need SPAPE router on only where you want to connect from. You see, there is no SPAPE router in these or these, because they're not connecting to anywhere. So it's only a one-way thing. So it only connects one way, but it doesn't know anything from the other side. It's just a simple connection. Yes. So it takes, the thing is that when the depending service, in this case header, is stopped, the calling service needs time to figure out that it's a stop, basically to catch the node down message. And this takes time. And if you have calls running all over the time, if you have requests, then they will fail, because there is a window which is not served because of the stopped node or stopped application. There's another optimization that is quite a low-hanging fruit, but we just never needed it. So now we monitor the node for the service, but we could monitor application controller instead. So that would reduce the same window, the same downtime window. Because when you do, the reason why, let's say you're running everything cheerfully and then you need to stop a node, you do init stop or something equivalent, then all the application stops one by one. After a while, the whole node stops. And only when the node stops, the node down message is sent to SPAPE router. That's a problem, because your application that you're interested in was stopped before the node was stopped. And that actually takes time to stop all the applications. So when the application, you want to remove the service when the application is stopped. There is one assumption that we make in our environment. One node is one service. This assumption drives the way we configure SPAPI router and the way we designed the configuration of SPAPI router. If you have another setup, this might work or not might work for you. But this is only the way that you configure it, not the way you connect or the way you react to events. So see that this might be or might not be applicable because of this assumption. We found this easiest to work with. I mentioned also that the environment is dynamic. So we support dynamic environment, and this is what we heavily do at Spil, especially with cloud computing and on-demand machines. How do we change the hosts that we connect? And we use Puppet for propagating the configuration files. Propagating the configuration files is not enough. You also have to ping your node that, hey, there's something changed. Do something about it. The canonical way to do this is a rel-up. We don't do rel-ups because we don't need to be running all the time. It's easier to stop and start the node and accept a few misses. But in SPAPI router case, you don't really need that. It's enough to update the configuration, the application environment, and call config change. Then it will figure out the change hosts and nodes and applications for you. This anything really, it's an application written by a colleague of mine in 2 days. The name is config changer. We didn't release it open source yet, but if there is interest, please ping me. It might be doable. It's very simple. So battle stories. So these are, I'll tell you some stories about the implementation of SPAPI router and the way we're running on production. This is not another Stalingrad. I heard battle all the time in this conference. I thought, what battles are you talking about, really? So now I'm the same. So first approach was we were trying to disconnect from irrelevant nodes first. It's very naive, but for our cases it maybe would have worked. So you connect to everything, see what's interesting, and then disconnect from what's not interesting. The problem with this is, what if there is one node interested, but the other one is not? So you connect, the other one sees, hey, there's some crap connected to me. Go away. Disconnect. Then the first sees, oh, I was disconnected. Retry. And then you see it's a really fight. And we had fun story with this. A single misbehaving component, so meaning a service, not a single node, but a component, brought the system down for a little while. That's one approach. We also had fully connected network experience. Due to a subtle bug in the library, we made a small change, non-obvious one, and it wasn't disconnecting properly after it figured out that there is no application running. So after a few hours, we noticed, oh, we have a fully connected network. Wow, over 1,000 nodes. So I would recommend to do that for everyone. You don't really understand what's going on until you see the network graphs of the machines. And thanks to off-peak, it was during the change was in the morning, and we noticed this in the noon. We had not that much traffic and 10 gigabit network cards, so we didn't have real downtime. We had sporadic issues. People were running around, but our users were still able to play games, thankfully. But this was a very good one.
Did you just say that you installed the fix at 3 a.m. in the morning?
No. In the morning.
Oh.
In the morning. So in the morning, you come in, you install it. This is how we do it. Our peak is 6 p.m. So 8 p.m. So and it starts growing like crazy after 12. So this is when we fixed it. Yeah. So a little bit of statistics, how this development and deployment came. So the initial version, tests actually, the first file were tests, was by Thijs Lau, my colleague. And the first production release was after a month. So that was 2012, January, February. Then a few features were added by Enrique Paf. So broadcast, the call all, and user callbacks. And after 2 years, within the 2 years, we added instrumentation, we fixed bugs, we changed the configuration, we changed the approach, and we used it heavily. And now, it's 9th. Oops, I got the date wrong. So public pre-release, we decided to announce it publicly for everyone to use. Yeah, this is not true, this is today. So SPAPI router source, documentation, and the paper, it's scientifically looking paper, how it works and why, is available online. Yes, this is a... So the next section is questions and answers. Questions and answers. Oops. I'll try to answer your question later.
Yeah, I'm very new to Erlang, so I just wanted to ask a few questions to see if I can clarify a little bit what was going on there. So basically, you have these routers in multiple places in your network. Is that right?
This SPAPI router is an OTP. It's a library, so like another application running beside your node. So if you run an application on your node, then you have also SPAPI router application. You know what's OTP?
But will you have, like, if you have a cluster, will you have one router in the middle of, or will you have multiple?
No. You have routers everywhere. So anywhere where you want to connect to somewhere, to another node, to a dependency, you have that router.
Right. So every kind of caller will have a router.
Yes, that's correct.
I see.
That's exactly how it works.
And how do the routers know where to connect and so on?
So this was the...
I'm sure you showed it, but I was kind of...
no, too far. Not here, not here, not here. Almost got it. Here. So this is how you show how to connect it. I'm very sorry if I wasn't clear enough. So let's do it again quickly. So you say that two hosts. Oh, that's better for you, I guess. So two hosts. It tries to connect to two hosts.
Okay, but you have the configuration.
Yeah.
You spread it with Puppet how to connect and so on.
Yeah. So
right.
API.
Okay.
API.
I think I get it.
Here. So this is my mistake. This is supposed to be main section or header. So this is your service that you're interested in. So A, you configure, then you get the network. B, you call it by specifying the service that you're calling. So imagine this is
and this is data that is stored in Puppet.
Yes.
Yeah, exactly.
Yeah,
I get it.
Yeah.
All right. So I guess this is great for service-oriented architecture and so on. Is there a cost without return as well, instead of just call?
Excuse me.
Is there a cost?
Of what?
This is a call.
Yes.
I guess it returns data.
Yes.
Is there a cost just to send data?
Sure. Yeah.
Don't care about.
Yeah.
Is there as well?
That's in the options in the 5 arity.
All right, I missed it.
This one. So
excellent.
You pass options async or
okay,
I don't remember precisely, but there is one.
It's in there. Okay.
Yes.
Excellent.
Yes, of course, over there.
So does it use distributed Erlang?
Yes.
And hidden nodes?
Yes.
Okay.
Yeah, I see you have more questions, so go for it. I should have stated this.
Oh, there, in the middle, of course.
You said that you don't care about race conditions. I was wondering why.
About this particular race condition.
No, you said you were describing some graph, I think, and at some point you say we don't. Of course, this will cause race conditions, but we don't care about it.
Okay, so let me remember where was it. It was in the connect and disconnect of the nodes. Yeah. Yes. Yes. So when you connect the final destination to your final node, you check what applications are running, and then you disconnect. So that's a race condition. Let me quickly recap.
Because the application might be just starting.
Yes. And then, but this is, yeah, exactly. Thank you very much. And after, there are these configuration items, the host monitor interval, world monitor interval, that every node will be rescanned anyway. So if there's something that you didn't connect, even though you had to connect, it will be connected eventually. And this is what we care about. So it's explicitly by, it's very good that you asked this. By these, this is patched, fixed on runtime. So if you connect it to something that you didn't have to. There was another question by this gentleman who asked about why do we run a node per Yeah, yeah. Because this is a better load distribution. Linux does quite good job in doing the scheduling, so we're fine with this. It's just there's no reason to do. Also, this gives very horizontal scalability, uniform. If you see that your whole cluster is not keeping up, you just add more nodes instead of trying to figure out which one uses most. More questions?
So if I understand correctly, the configurations, the nodes are dynamic, but the hosts are static. So if you need to add a new machine or something?
Yes. So this thing does not do host discovery. Okay. You have to explicitly give hosts. So, and there are many ways to do it. You can have another component which generates the configs.
But can you add a host in real time, or you need to stop the node?
No. You add the host on real time without stopping your application, and then you run SPAPI router application config change, and then the change propagates.
So if you did something like NetADM world on a new module, because you think, I just want to put this in the cluster somehow, does your SPAPI router need to be updated to have that host in it as well?
So if you connect with...
So you've got your network with loads of nodes in it, and you add a new network to it manually with NetADM.
Yeah,
or whatever.
You add a new host.
Yeah.
Okay.
Do you then need to update your SPAPI router everywhere to make it use it? Because
yes.
It will disconnect immediately? Well,
the way it works now, it's, well, we made the decision that SPAPI router takes care of everything. So if you add extra stuff, it's probably going to be disconnected. If you add extra stuff without telling SPAPI router, and you connect to something that uses it, then you're going to be disconnected. It's a conscious decision to keep on control in one place. So we never do manual connections for that reason, that we just don't know. You know, there has to be someone taking care of it. So we made a decision to make it automatic.
So how do you handle a partition where something starts up, SPAPI router isn't aware of it, so it disconnects it. Yeah. Then the config's updated and SPAPI router reconnects it.
The configs are not, the configs, we make the configs, meaning the people who are building the cluster make the configs. The configs are not inferred by the way the current network looks like.
Right.
So we make the decision how the network looks like, make it that way, and make the configuration that way.
I understand. Okay.
Oh, I have to jump over the chair again. Okay.
So you mentioned that the battles or the armies are heterogeneous, and there's like, you know, fleets and whatever, you know, Air Force and stuff like that. I know you're an Erlang shop, but is there any plans in the SPAPI router to support heterogeneous services? Because in SOA, or service-oriented architecture, there can be many services in different languages and different sort of platforms and stuff like that. Is there any support for SPAPI router to support that? So calling into like, I don't know, God forbid, Java service or something like that?
Very good question. So you have RabbitMQ for that, which exactly does this. And you have Cloudl. I never figured, is it an uppercase I or is it an L? So you have Cloudl, let's assume it's I, which exactly does what you're describing. And the reason why we made this component, we didn't want to get out our calls from the Erlang environment. So we have, in our backends, we have only Erlang network, communicating message passing using protocol buffers for compatibility. And we just don't have to get out of that environment, and we don't support anything. So we have also a fair question. We have a few things that are still running from the old days in PHP or Python. These are also in our architecture. But these services have wrappers in Erlang. So there's an Erlang node, and just behind it there's the PHP or Python or whatever, which communicates in that way. So SPAPI routers, there's no reason to support other things because that's not the way it's for.
Just a question, your design decision when you made this. As you stated, the problem that you have is that you have in excess of 100 nodes, basically. And the fully connected network there means that you're running into blow-up in connections. Why didn't you try to do a tiered architecture where you would have one router per node and then having that consolidate all the services on a single node, on that host.
I didn't fully understand. So you have
So you would have a router on the host,
yes,
and then actually consolidating all the services on that node into that single router on that node.
So then the local services communicate to each other through that router, or?
Exactly. And then you would have the services, all the definitions in that router, which would be a distinct feature of that host. Just a question, because then you actually get away from all these connectivity problems.
I need a minute. I need some more time to understand what you're proposing. It doesn't really fit to my head that quickly.
So you have a routing service on the host.
Yeah,
that would be the SPAPI router, right? And then you would have the services on the Erlang nodes on that host.
But we have more than one host.
Yeah, but you only have like a dozen. That's 12. Fully connected 12 nodes is not a big deal.
Oh, you're proposing to make islands.
Yes.
Okay.
Now I'm just asking why you didn't opt for that solution, because it seems quite straightforward.
So yeah, we had this. We were considering this to have a full vertical stack on a single machine, and this is actually what we have. But I cannot tell you now why we didn't do it. There was a reason for this, but I don't remember why I didn't do this. It was one of the ideas how to make this happen. But let's have a chat later. I'll try to remember. It was a long time ago also.
Could you possibly say something about your distribution of your application? Because if I understand correctly, the router doesn't need to be on every host for what reason. Do you deploy everything explicitly where it has to live, or how do you handle that?
Okay, so we have a bunch of machines, and the way we deploy, I'll give you a broad answer that will likely answer the question. So we have a bunch of machines. We deploy services gradually. So most of the services we deploy on half machines. So shut them down, deploy a new version, bring them up again. Everything's fine, and after half a minute or something, we deploy the other half. The backend, like I told you, we have around 50 services. So every machine has all the services inside. Ideally, that's the full vertical slice. That's not actually, that's another answer to your question. That's not actually true. Not all services are living on the same host. Some of them, for instance, we have database services. We have distributed database services, which are dedicated per, for instance, 5 machines, a cluster of 5 machines, dedicated to a particular distributed database. That's also, then we take care of that also explicitly. Yeah. I understand your question now, and this was one of the reasons why we didn't do it that way, because we had more of these, not only databases, but also stuff in PHP and Python and everything.
Final question, unless it's a Java question, and then we won't have it.
Only problem I see this is but maybe your particular case is not that big, but again, not putting like any offensive or anything, but we at Spotify, we have roughly 7 data centers. So we built a similar thing across data centers, and the only problem I see in your implementation is that Erlang messaging node to node, it's not that good over unreliable networks or between data centers. Do you have any experience with that, or how do you manage that?
Yes, we do have experience with that. We don't do that. If we need to send something to a different data center, there are much better ways to do it than Erlang distributed message passing, like you just pointed out.
Good. Let's all thank Motiejus.
Thank you.
And remember to vote. Remember to vote as you leave the door.